start with this. Someone asked me how to find the derivative of x plus 3 to the x plus 3 power, or something very similar to that. So there's actually two valid ways of doing a problem like this. I feel like the way that is maybe simpler, at least writing it out right, is to rewrite this as the derivative of e to the natural log of that same expression. Right? If you're working with anything really, something is always equal to e to the natural log of that same thing. So we can then use the properties of logarithms to rewrite this exponent, the natural log of x plus 3 to the x plus 3. That x plus 3 can come down in front, and we can rewrite this as the derivative of e to the x plus 3 times the natural log of x plus 3. And now we can differentiate that. We know the derivative of e to the x is e to the x. We know the derivative of e to the stuff is e to the stuff times the derivative of the stuff. So the derivative here is going to be, so I'm going to get e to the stuff again. That just reoccurs. And then we're going to multiply by the derivative of that stuff, or the derivative of that exponent. So let's write it out that way. So that's going to be, I'm going to take the derivative of x plus 3 times the natural log of x plus 3. Okay, let's do two things in the next step. Thing one, we're going to rewrite e to the x plus 3 times the natural log of x plus 3 as, well, this is equal to this is equal to this. So those are the same. We're going to rewrite this as this. It's not absolutely necessary, but it is pretty typical. So I'm going to say, oh, that's just x plus 3 to the x plus 3. Then we're going to multiply that by the derivative of this stuff. So we're going to use the product rule. We're going to get x plus 3, or sorry, the derivative of x plus 3, which is 1 times the natural log of x plus 3. Plus, now we're going to get x plus 3 times the derivative of the natural log of x plus 3. The derivative of the natural log of some stuff is 1 over the stuff times the derivative of that stuff, and the derivative of that stuff here is just 1. So simplifying just a tiny bit, this is equal to x plus 3 to the x plus 3 power times natural log of x plus 3 plus 1, right? This simplifies to 1, so yeah, x plus 3 divided by x plus 3. And that's one of the two ways you can find this derivative. I can do it the other way if you guys want to see that, but someone will have to say they want to see it. Otherwise, I will not do it that way, and we'll just go on to something else. Does anyone want to see the other way of doing this? Great. Okay, yes, fair enough. I'm happy to do it. Got a few yeses, so yes, totally. One yes is enough, but more yeses is like, yeah, okay, fine, we'll do it. So here's the other way you can do it. You could write it as y equal to x plus 3 to the x plus 3 power, and then take the natural log of both sides. The natural log of y equals the natural log of x plus 3 to the x plus 3. And then just like in the previous problem, we're going to use the natural log rules to bring that x plus 3 down. So we're going to say natural log of y equals x plus 3 times the natural log of x plus 3. So then we'll differentiate. Here the natural log of y is 1 over y times y prime. And then for this right-hand side, we're going to use the product rule just like we did for the other problem. Derivative of x plus 3 is 1 times the natural log of x plus 3 plus x plus 3 times the derivative of the natural log of x plus 3, which is 1 over x plus 3. Bringing the y over, we get y prime equal to y times the natural log of x plus 3 plus this part just becomes 1. And then finally, replace y with what it's equal to, which is x plus 3 to the x plus 3. And you get x plus 3 to the x plus 3 times the natural log of x plus 3. Just like we did on the other side. So either way you do it, you're going to get the same answer, assuming you simplify it to the same extent. It's really just a matter of either your preference, or it could be a matter of what your teacher would prefer you to do. But if it's up to you, you should pick whichever way seems easiest to you. Let's look at a couple of exponential growth / decay questions. I guess I should erase the other one. So someone asked a question similar to this, although their version was a tiny bit easier. Actually, I decided to make it a little harder. So here's the question that somebody asked, or a version of it. You're given the function y equal to c e to the k t, and you're also given that it passes through the following points. It passes through. I'm going to do the slightly easier version first, and then we'll see if we can make it work. It passes the points 0, 5, and what do we got here? 6, 19. Okay, so you can start with either one, but it's worth knowing that specifically if you're given the 0 for your t value or your x value, it's t in this case, it could be x. You should probably use that point first. It's going to be easier to manage. So I plug in 0 for t and 5 for y. I get 5 equal to c e to the k times 0. Well, that's nice because k times 0 is 0 and e to the 0 is 1. So 5 equals c times 1. So c is equal to 5. Great. Now we're going to go back and we're going to modify. We say, okay, now I've got y equal to 5 e to the k t. And then we're going to plug in our other piece of information, where t is 6 and y is 19. So 19 equals 6 e to the k times, sorry, not 6, 5 e to the k times 6. Now we're going to solve for k. So we get 19 fifths equals e to the 6k. Take the natural log of both sides. So natural log of e to the 6k is going to be 6k. And then finally divide both sides by 6. So k equals the natural log of 19 fifths over 6. So our final answer is y equal to c, sorry, plugging in c, we get 5. Y equal to 5 e to the k, which is this mess, natural log of 19 fifths over 6 times t. That's how we write that. I will, no, I don't think that's what we're doing. This problem could be harder, specifically if they didn't give you one where it was 0 for your t. Here's what I mean. Let's say we had the same setup. But they gave us that instead of having those 2 points, now it passes to the points, what did I write down here? 1, 6, and 3, 24. What's challenging about this problem versus the previous problem is you can't just find c right off the bat. So if I plug in 1 for t and 6 for y, I get 6 equal to c e to the k times 1, which is just k. And I actually can't really solve, right? I won't find out for sure what c or k is yet. So all I can really do at this point is use the other piece of information, which is that if t is 3, then y is 24. So 24 equals c e to the k times 3, or 3k. Okay, so what do we do now? Well, typically what we do now is we solve both of these equations for c. And then we set those equal to each other. So isolating c here, you get 6 over e to the k equals c. And isolating c here, you get 24 over e to the 3k equals c. And then we can set those equal to each other so that we get 6 over e to the k equals 24 over e to the 3k. I would probably cross multiply here. 6 e to the 3k equals 24 e to the k. I'm going to divide both sides by 6 and by e to the k. So I divide both sides by 6, I get e to the 3k equals 24 divided by 6 is 4 e to the k. And then if I divide both sides by e to the k, I get e to the 3k divided by e to the k equals 4. E to the 3k divided by e to the k, we subtract those powers, and 3k minus k is 2k. So I really have e to the 2k equals 4. Take the natural log of both sides. 2k equals the natural log of 4. So k equals 1/2 natural log of 4. I would actually simplify that even further, specifically because 4 is a square number. I can write 1/2 natural log of 4 as the natural log of 4 to the 1/2 power. The 1/2 power is just the square root. So that's the natural log of the square root of 4, which is just the natural log of 2. So we end up with k equal to the natural log of 2. And then we can use either one of these equations to find c. If I plug it in here, c equals 6 over e to the natural log of 2. Can anybody tell me what nice integer number that is? If it was in class, I would ask me to show you on your hand, and you would only need one hand to tell me what that number is. All right, it's okay. You're very close person who messaged me. And so I should mention, just so, in case not everyone's aware, you can always send me a private message if you don't want everyone to see your answer. That's perfectly fine. Sometimes my friend was telling me, yeah, exactly, totally. Yes, the person who just wrote me now has it correct. Yeah, the denominator is 2. E to the natural log of 2 is just 2. So 6 over 2 is 3. And you actually do get the same thing if you do it here, which you should, right? You should get the same either way. If you did 24 over e to the 3 times natural log of 2, e to the 3 times natural log of 2 is, well, clearly we should use this one because it's easier. If you did it this way, e to the 3 times natural log of 2 is e to the natural log of 2 to the 3rd. E to the natural log of 8 is just 8, and 24 over 8 is also 3. So our final answer here would be that y is equal to 3 e to the natural log of 2 times t. Although I should mention here, especially, you could rewrite this. You could say, oh, this t times natural log of 2, this is really equal to 3 e to the, right, if I think of it as t in front times natural log of 2, the t can come up as a power. That's the natural log of 2 to the t. And then e to the natural log of a thing is just that thing. So e to the natural log of 2 to the t is just 2 to the t. So another valid way of writing this would be 3 times 2 to the t. I want to stress this is not equal to 6 to the t. Right? You can't just multiply the 3 and the 2 because the 2 is to the t power and the 3 is not. That's all I really didn't want to spend too much time on exponential growth and decay. So I'm going to leave it at that, but if you guys want, we can circle back around to that later. So let's go ahead and move into talking about antiderivatives. Oh, I should also mention though, someone did in their reflection ask me a question about the question was like 1 gram of radium, that you have 1 gram of radium and will you have more than half a gram after 1,000 years? And I feel like there's some other piece of information about that question that we need to have to be able to answer it. Like either we need to know the half-life or we need to know some other amount of radium at some time. If that was you, feel free to send me a message and let me know if there was more information. Otherwise, I don't really know how we would answer it, other than Googling what's the half-life of radium. Interesting. Yeah, so I don't know. I mean, sometimes I will certainly admit occasionally, people, myself included, make mistakes when they write questions. They kind of forget to include important pieces of information. So I'm just going to Google the half-life of radium here. Radium is 1600 years. So this question actually is almost too easy if we know the half-life. So the radium half-life is 1600 years. Okay, so here's what that means for us. It means that and I like to make a little table. Time and then amount. So we know that at the beginning, time equals 0. We have 1 gram of radium. And then we also know that 1600 years later, well, 1600 years is a half-life, so we're going to have half the amount we started with, 0.5 grams. The question is, or the question was, will we have more than half a gram after 1,000 years? Sure, yeah, 1599 or 1600, either way, close enough, right? Close enough. So the question is, after 1,000 years, will we have more than half a gram? And the answer is yes, right? Because as time goes on, the amount of radioactive isotope decreases. So we start at 1 gram, we have less down to half a gram. So between year 0 and year 1600, you have between 1 gram and half a gram. So certainly at year 1000, right, the amount is less than 1 gram, but it's definitely greater than half a gram. So I believe the answer to that question is yes, right? We're going to have more than half a gram of radium after 1,000 years. But again, unless the intent of this problem was for you to look up the half-life or just know the half-life of radium, it seems not particularly well developed. But hey, so yeah. Actually, just to piggyback on this, so let's use 1600 just because it's easier to work with than 1599. Let's say we were given a slightly different setup. Let's say that we know that we're starting with, let's say we have initially, let's say we have 6 grams of radium. And I want to know, yeah, sure. Will I have, I'm going to ask this more like the typical way. How much radium will there be? Will remain. That's not the way I want to phrase that question. Sorry. How long until only 2 grams remain? Okay, so this question does require us to do some work. And it requires us to do the typical work, which is starting with the model for radioactive growth or decay, sorry, exponential growth or decay, y equals c decay t. And again, I do like this table. Right, here's my table, time and amount. The amount is y. So we know at time equals 0, we have 6 grams. And we want to know at what time we have 2 grams. Now, here's the thing. Most of the time when you're solving a radioactive decay or an exponential growth problem, you need 2 points of data. I have 1 point of data written down so far. At time 0, I have 6 grams. But we also have another point of data if we remember that we know the half-life. So we're given, let's pretend that we're given the half-life is in fact 1600 years. Because we're lazy and we don't want to deal with 1599. Well, that means that 1,600 years later, we have an amount that's half of what we started with. Great. Now we have enough data points to solve the system. So I'm going to find C first, and C is always going to be the amount you have at time 0. So if you know what time 0 is, you know that C is going to be 6. We can also do the work, right? We could say, okay, the time 0, y is 6, so 6 equals C e to the k times 0. But 0 times k is 0, and e to the 0 is 1, and 1 times c is c. So you get 6 equal to c. Great. Then we're going to rewrite our model, y equals 6e to the k times t. And then we're going to, so I should say, right, we plugged in this piece of data here. Now we're going to plug in this piece of data to get our other equation. We're going to get y is 3, and t is 1600. And now we're going to solve for k. So divide both sides by 6. 3 divided by 6 is 1/2. By the way, this always happens. When you're using the half-life to find the k value, you're always going to get 1/2 on the left equal to e to the k times whatever the amount of time the half-life actually is. Always, always, always. Take the natural log of both sides. Natural log of 1/2 equals the natural log of e to the stuff is just the stuff. So natural log of e to the k times 1600 is just k times 1600. I want to make sure everyone's cool with that. I'm going to write it over here, right? The natural log of e to the k times 1600 is just k times 1600. Solve for k, so divide both sides of 1600. So you get k equal to the natural log of 1/2 equal to 1600. You might have seen this before in chemistry, right? That the k value is always the natural log of 1/2 over the half-life, or vice versa. The half-life is always the natural log of 1/2 over the k value. It comes up in chemistry right for them. So now our model is y equal to 6 e to the k, which is natural log of 1/2 over 1600. So great, we found the model. Now we have to use the model to answer the question. And the question was, how long until only 2 grams remain? Another way I could have phrased this question would be how long until 2/3 of the amount has decayed, right? Because 2/3 of 6 is 4, it would have lost 4. That's a much less nice way of phrasing it, but it's something you might run into. So something to remember, if they tell you how much is decayed, so the language here is kind of terrible. Let me actually finish this, and then we'll talk about how the language can be awful. And so I'm going to set this equal to 2, right? Because I want to know. This is why I like this chart, by the way. So I'm like, oh, I'm setting y equal to 2, and I'm solving for 2. I set y equal to 2. I'm going to get 2 equal to 6 e to the natural log of 1/2 over 1600 times t. Divide. You're always dividing by this coefficient first. So divide both sides by 6. 2 divided by 6 is 1/3 equals e to the natural log of 1/2 over 1600 times t. Take the natural log of both sides. Natural log of 1/3 equals the natural log of e to the stuff is just the stuff. So it's going to be the natural log of 1/2 over 1600 times t. It's kind of dying. And then let's put it there. Multiply both sides by 1600. Divide both sides by the natural log of 1/2. So you get 1600 times the natural log of 1/3 divided by the natural log of 1/2 equal to t. That's our answer. And then you could use a calculator if you wanted to get a more. In fact, we probably should just kind of answer the question. So my guess would be it's going to be somewhere between 1600 years and 3200 years. Because after 1600 years, you get 3 grams. And after another 1600 years, you get half of 3 grams, which would be 1.5 grams. So let's see. If we calculate this, we're going to get, let's see, natural log of 1/3 times 1600 divided by the natural log of 1/2. We're going to get, let's see, 2,536 years approximately. Okay, the last thing I want to say about this, just to kind of be, to kind of point out something about the language. So let's say we started with 10 grams of some substance. Uranium. Okay. The following statements all mean the same thing. How long until 2 grams remain? How long until we decay? And how long until it decays to 2 grams? There's like 2 more things I want to write. How long until it decays by 8 grams? So I find these 2 the most confusing, right? If you say it decays by 8 grams, it means you've lost 8 grams. But if it decays to 2 grams, you're just saying you've lost enough to get to 2 grams. And I've definitely written questions like this before, and then I've been like, that was terrible. It's really confusing language-wise. So these all kind of mean the same. These all exactly mean the same thing, and be careful with reading them. Yeah. So just want to point that. I didn't really have another one. I thought I did. All right. I think I've said enough things about other things. Let's talk about antiderivatives. And so the main thing to remember about antiderivatives is they undo a derivative. Right? If you know the derivative of a function, you know the antiderivative of the derivative you just found. So for example, we know that the derivative, let's just pick something easy, the derivative of x to the 6th is 6x to the 5th, for sure. We also now know that the antiderivative of 6x to the 5th, the x, and well, let me actually say, is equal to x to the 6th. Well, not just x to the 6th, right? It could be x to the 6th plus 1, or plus 7, or plus 1 billion, or minus 5, or minus pi, right? It could be plus any constant. So antiderivatives are unique up to a constant, meaning that it's always going to be x to the 6th, and then you could have plus whatever constant you want. But there's no other way of finding the antiderivative of 6x to the 5th. It's exactly this piece, and then plus whatever constant you happen to want. A couple things about this notation. So this just means antidifferentiate. The antidifferentiate the variable x with respect to x. That, let me see, I'm trying to think here. When we get into double integrals, we actually, we do in 16C, then it kind of matters. But for now, the d whatever here, the d variable, that variable should always match whatever variables are in the integral. So it's just telling us find the antiderivative. I also want to point out, after you find the antiderivative, you no longer need to write this symbol. Just like after you find the derivative, you no longer need to write this symbol. So this symbol, right? This symbol means differentiate. This symbol means antidifferentiate. And they undo each other. If you antidifferentiate and then differentiate, you're going to get back the same function you started with, right? If you antidifferentiate 6x to the 5th, and then you differentiate x to the 6th, you get back to the function you started with. Or vice versa. If you differentiate x to the 6th, and then anti-differentiate what you got there, you get back to what you started with, plus a constant. So the real kind of key thing to keep in mind when you're talking about antiderivatives is that derivatives and antiderivatives undo each other. One of them does something, the other one undoes it and gets you back to the function that you started with. Let's see here. Okay. So there are some rules for antiderivatives. The one we're going to use the most being, not the most, but the one we're going to start using the most being what I like to call the anti-power rule. So let's look at an example. I want to find the antiderivative of x to the, I don't know, let's say x to the 8th. So I'm looking for a function whose derivative is x to the 8th. Well, we know when we take derivatives, the power becomes 1 less. So I'm probably looking for something like x to the 9th. But the derivative of x to the 9th is not quite what I want. The derivative of x to the 9th is 9x to the 8th. And I really just want x to the 8th. So what could I do to both sides of this equation that would make the right side equal to x to the 8th? What could I maybe divide by? My fan's really loud here. Right, I could totally divide by 9. And here's the thing. Dividing by a constant, or you could also say we could multiply by 1/9. Multiplying a derivative by 1/9 doesn't change it. I mean, it changes it by you multiply by 1/9, but it doesn't change the process. So I can say, oh, the derivative of 1/9 times x to the 9th is, well, it's 1/9 times the derivative of x to the 9th, which is 1/9 times 9x to the 8th, which is x to the 8th. So the derivative of 1/9 x to the 9th is in fact x to the 8th. So the antiderivative of x to the 8th is in fact x to the 9th divided by 9 plus a constant. More generally speaking, one of these blue pens have any life in them still. Yeah, there we go. More generally speaking, the antiderivative of x to the nth power, this pen is some better days. I think I might have to. Yeah, let me give myself some new ink here. It's time for new ink. Oh. Sorry. All my pens. Okay, you're done. 1 second. Should have done this ahead of time, but thought I still have pens with life in them. Okay, so the antiderivative of x to the n is equal to, so just like the antiderivative of x to the 8th was x to the 8 plus 1 divided by 8 plus 1, the antiderivative of x to the n is x to the n plus 1 divided by n plus 1, also constant. Now there is one exception to this rule. Can anybody tell me what value of n might not be so great here? Right. N can't be -1 because if n is -1, we've divided by 0. That's a problem. So here's what that means. It means for any power of x, we know the antiderivative, except for the moment, we don't know the antiderivative of x to the -1. We'll get there probably, maybe today, maybe tomorrow, I don't know, Thursday. You might already know it, but we'll leave it alone for now. So here's our anti-power rule. If you're anti-differentiating x to any power, you're just going to add 1 to that power and divide with any power. And it's exactly because the derivative works. Right? If you take the derivative of x to the n plus 1 over n plus 1, I don't usually write the plus c when I'm taking the derivative because I know the derivative of plus c is 0, but let's go ahead and write it. That derivative is going to be, well, I'm going to rewrite this as the derivative of 1 over n plus 1, which is a constant, times x to the n plus 1 plus c. The derivative of a constant times a function the constant just hangs out and multiplies the derivative function. The derivative of x to a power is that power times x to the 1 less power. And n plus 1 minus 1 is just n. And the derivative of a constant by itself without being multiplied by any function of x is just 0. And look, the n plus 1s cancel out, and you totally get x to the n. So the derivative of 1 over n plus 1 times x to the n plus 1 is equal to x to the n. The antiderivative of x to the n is x to the n plus 1 over n plus 1 plus c. So great, we can use this rule to do all sorts of things. So here's kind of like the number one rule of thumb. If you can write something as x to a power or your variable to a power, then you can antidifferentiate it by using the power rule. So let's look at a couple of examples. Let's look at something like this. Let's look at x to the 9th plus the square root of x plus 1 over x cubed plus 7. It's a lot in here. It's good to talk about. So before we antidifferentiate, it's really going to be in our interest to write everything as x to a power. So I want to write this as, well, this is x to the 9th. Square root of x is x to the 1/2. 1 over x cubed. So here's the thing. You cannot say the antiderivative of this is 1 over x to the 4th over 4. Right? Because you don't just have x to a power, you have 1 over x to a power. We really, really need to rewrite this as x to the -3. 7, you could write, if you really, really wanted to, you could write it as 7 times x to the 0th. I think that's kind of not necessary, but we totally could. I'm going to talk about how you don't need to in a second. So let's antidifferentiate this whole thing. We're just adding 1 to the powers and dividing by many powers. So we're going to get x to the 10th divided by 10 plus x to the, if you don't know how to add right away, you can just write it's x to the 1/2 plus 1 divided by 1/2 plus 1. And then we can do the addition to the next step. -3 plus 1 is -2. So just a reminder, when you add 1 to a negative number, it's going to get less negative. And then finally, now here's what I really want to say. When you antidifferentiate a constant, you just get that constant times x. Right, so the antiderivative of 7 is just going to be 7x. If you want to look at it this way, you can say, oh, it's going to be 7x to the 0 plus 1 divided by 1. So it does work. Plus c. But really, right, we know that the antiderivative of any constant, if you antidifferentiate a constant, you're going to get that constant times x plus some other constant. Because the derivative of a constant times x is just the constant. Okay. And then we should simplify our answers just a tiny bit. This is x to the 10th over 10. This is x to the 3/2 divided by 3/2. But if we're dividing by 3/2, we should flip and multiply and say we have multiplication by 2/3. Here I would write this as minus. Now I personally like to have my powers of x being positive, so I write this as minus. I would bring that x to the negative second down as x to the positive second, so it'd be something over 2x squared. Well, I brought this down. There's still a factor of 1 left on top. And finally, this is just 7x. So that's how we'd antidifferentiate something like that. Questions? Let's see here. You guys are right. No, you might be right. Okay. So again, I'm going to reiterate. The name of the game is make sure you can write all of your things as just x to a power. Not 1 over x to a power, not some other weirdness. Oh, go back, please. Sure. Yeah. No problem. So let's look at something like this. Someone asked me one like this, although I see 2 problems that are very similar, so I'll do both of them. So one person asked this question. I'm going to change the numbers a little bit just so I'm not exactly doing homework problems. Someone asked something like this. It was essentially 6t to the 4th over the cube root of t. And then someone else asked it, but it looked a little different. Someone else asked one that looked like, oh, sorry, I'm missing something here. I'll go back and fill it in a second. 6t plus 4 over the cube root of t. We can certainly, and we will do both of these, but I just want to point out, right, I feel like only one of these was actually a homework question or similar to a homework question. That's fine. Either way, we want to simplify this. So if you've got a fraction, a rational or not, it's actually technically not a rational fraction. What you want to do is you want to divide your, right here we just want to divide. So I can rewrite this as the integral of 6t to the 4th over t to the 1/3 dt. And then to simplify this, t to the 4th divided by t to the 1/3, I'm going to subtract those powers. So I'm going to get the integral of 6 times, let's see, 4 minus 1/3. Well, 4 is 12/3 minus 1/3. That's going to be 11/3. So I have 6t to the 11/3. I will also mention, just like with derivatives, with antiderivatives, constant multiples can kind of get pulled out. You can say this is really 6 times the integral of t to the 11/3 power. And now I'm just going to use the antipower rule. This is going to be 6 times t to the 11/3 plus 1. 11/3 plus 1 is 11/3 plus 3/3, which is 14/3. Divided by 14/3. But we know that when we divide by a fraction, we can just flip and multiply. And that's pretty standard practice. When you say, oh, I've got 11/3, you typically see people write the next step as t to the next power multiplied by the reciprocal of that power. We should do one simplification here. 6 and 14, we can reduce that to 3 and 7, right? We can cancel a 2 in each of those. So we're going to get 9/7 t to the 14/3 plus c. The same sort of advice also is true for this problem. So whenever you have some sort of fractional expression that just has constants or powers of t or whatever your variable is, if your denominator has one single term, meaning it's not like the cube root of t plus t or t squared plus 5, or as long as it's just one thing that isn't adding or subtracting anything else, you can divide each thing in the numerator by that one thing. So we're going to say, oh, I'm going to rewrite this as 6t over t to the 1/3 plus 4 over t to the 1/3. And then we're going to rewrite it so that all of our powers are in the numerator. Here, t to the 1st divided by t to the 1/3, we're going to subtract those powers. And we're going to get 6t to the 1 minus 1/3 is 2/3. Here, there isn't a t on top, so we're just going to bring this t up to the numerator and change the sign of it to being 4t to the negative 1/3. And now we're going to antidifferentiate. We're going to add 1 to the power, so we're going to get t to the, let's see, 2/3 plus 1 is 5/3, because it's 2/3 plus 3/3, which is 5/3, times 3/5. Usually I write it in front, but I didn't want to enough space. Plus 4 times, let's see, t to the negative 1/3 plus 1 is t to the 2/3. Divided by 2/3 is the same as multiplying by 3/2 plus c. And we should simplify. 6 times 3/5 is 18/5. T to the 5/3. 4 times 3/2 is going to be 12/2, which is 6. T to the 2/3. Let's do another one. Let's do one that looks like, sure, looks like this. Oh, not that. Let's do that. Let's say we want to do the integral of 6x to the 5th plus 5x cubed minus the square root of x plus 1 all over x squared. Yes. Now, personally, I prefer to do it like this, where you're dividing each thing by the denominator. But I'll also point out, some people like to write it like this. The integral of 6x to the 5th plus 5x cubed plus, I'm always going to change my roots to fractional power. So cube root of t is t to the 1/3. Square root of x is x to the 1/2. Oh, sorry, it's minus, they're not plus. And instead of dividing by x squared, we can say that's multiplied by x to the -2. So that has to distribute to each of the 4 terms. So that multiplies that, multiplies that, multiplies that, multiplies that. And when you multiply two things together, you add their powers. This is going to be still, I still haven't integrated yet, I'm just simplifying. This is going to be the integral or antiderivative of 6x to the 5th times x to the -2nd. We're going to add the powers, so we're going to get 6x cubed. And 5x to the 3rd times x to the -2nd. 3 plus -2 is 1, so you get 5x to the 1st. 1/2 plus -2 is 1/2 minus 2, which is -3/2. So we're going to get minus x to the -3/2. And 1 times x to the -2nd is just x to the -2nd. So that's also a perfectly fine way of doing it. You're going to get the same thing either way, right? If you divide these, x to the 5th divided by x squared gives you x to the 5 minus 2, which is x to the 3rd. And this one you get x cubed over x squared, which is x to the 1st. So it's the same result either way, just do whatever is more comfortable. The one thing I want to point out is I've seen people do it this way and then kind of just, and then somehow it becomes this plus this minus this plus this minus this, right? They don't multiply it through. So if you're going to do it this way, you have to make sure you multiply this piece through to each of those other pieces. So that's going to be 6x to the 4th over 4, right? Just using my anti-power rule, plus 5x squared over 2, minus, I'm going to leave myself a little space here, x to the, let's see, -3/2 plus 1 is -1/2. Divided by -1/2 is the same as multiplying by -2. And then we're going to get plus x to the add 1, so -2 plus 1 is -1 divided by -1. And then we should simplify. 6 over 4 becomes 3/2 x to the 4th plus 5/2 x squared plus 2. So you could write 2x to the -1/2. You could write 2 over x to the 1/2. I would probably write it as 2 over the square root of x, to be perfectly honest. And then here, the x to the -1 comes down to the bottom as divided by x, so you get plus 1 over -x. But really, I should pull out the -1 factor and write it as -1 over x. You might notice that from here to here, I wrote it slightly differently. Here I wrote it as 5x squared over 2. Here I wrote it as 5/2 x squared. Either way is fine, and neither one is particularly preferred. I just decided to write it differently. There's no really good reason for that. Okay, so powers of x. Let's see. I feel like there's a few other things here. That's a good one too. We should do that one. Yeah, let's look at a few more. It's good to practice these. Actually, let's look at one that. Let's look at take a quick little jaunt to the side here for just 1 second. What if instead I asked what the integral of, say, I don't know, e to the, not yet. I wanted to do x to the 5th plus e to the x minus cosine of x plus so yes, this is not just powers of x, here's what I want to point out. All of these things are functions that we should be able to recognize as the derivative of something we already know. I know that x, well, we know how to deal with the powers of x, right? This is going to equal x to the 6th over 6. Okay. We know that e to the x is the derivative of what function? You guys all know this one. What's e to the x the derivative of? Right, e to the x is its own derivative. So e to the x is the derivative of e to the x, and the antiderivative of e to the x is e to the x. Okay. What function has a derivative that is negative cosine? Well, let's just what function has a derivative that's cosine? Well, let's see, the derivative of sine is cosine. Exactly. So the antiderivative of cosine is sine. So it's basically for sine and cosine, it's the opposite positive or negativeness. I know the derivative of cosine is negative sine. I know the antiderivative of cosine is positive sine. It's only for sine and cosine, though, not the other four trig functions. We also know a trig function whose derivative is equal to secant squared. Anyone want to tell me what it is? Yeah, exactly. It is definitely tangent of x. So I just want to really, really, really stress, if you know that that thing is the derivative of something you already know, you know its antiderivative. In fact, I'm going to throw another one at you. We also know, well, yeah, there's more to say about this. For now, I'm going to write this, although technically I'm leaving something off. The antiderivative of 1 over x, we talked a lot about a function whose derivative is 1 over x. In fact, we talked about it today, like in the first couple questions we did. Whose functions has, yeah, exactly. Now, we'll get into this a little bit later because I don't want to get into it right now. But technically, the antiderivative of 1 over x is not just the natural log of x. It's actually the natural log of the absolute value of x. I will explain this later. Don't worry about it right now. It's not a huge deal, but it is something that is important to remember. So when you're anti-differentiating this, you really do need those absolute value symbols around the x. Let's do some more practice. It's all practice. Yeah, let's see. Oh, someone asked me this question, which I thought was a good one. And again, I'm not sure because of the way it was written in their reflection, it wasn't super duper clear to me which way it was meant to be. So let's just do it like this. Yeah, I don't know. Let me take a look here. Nope, I don't see. Wow, it looks like for. So let me ask you: have you guys I guess homework 2 for Lee is due today? Yeah, that seems correct. Curious about something. Let me see. Because okay, fine. Dumb. Just want to see the thing. Sorry, I was looking at his homework 3, and homework 3 for Lee seems to be all about u-substitution, but I guess we're not quite there yet. So let me just take a quick gander at homework 2. Sorry. God, homework 2 is the long, holy smokes, that's a lot of problems for homework 2. 38 problems. Wow. Yeah, right? Yeah. I mean, I will certainly say it is a lot of problems, but the way most of us learn math is by doing the problems. Oh, Moz class is a midterm on Friday. Good to know. I did not know. Oh, yeah. Wow, that's a lot of. Okay. Okay, cool. Yeah. All right. Well, I guess. All right. Okay, cool. I found the problem I was looking for. So here's the problem. It's like literally the last problem that someone asked me. So here's my version of it. f prime of x is equal to x to the fifth minus 9 over x to the fifth. And we are also given that f of 2 is equal to 4. And we want to find f of x. So this is what is commonly referred to as initial condition problem or initial value problem, where in addition to finding the antiderivative, which usually has a plus c, we're then going to use this initial condition to solve for that constant c. So that's all. When you see a problem like this and you're trying to find the antiderivative or find the original function, if you see something like this, you should just say to yourself, oh, I know that means I have to solve for the constant c. That's all that this information is really saying. So we're going to do the same process. And in fact, before I do the same process, I'm going to rewrite this. So I'm going to say that f prime of x, just like I did in the previous problems, I'm going to divide each thing by x to the fifth. And then I'm going to rewrite them. X to the fifth over x to the fifth is 1. And 9 over x to the fifth, I need to write so that it's 9 times x to the negative fifth. And now we can antidifferentiate these. So f of x is going to be the antiderivative of f prime of x, which is going to be the antiderivative of 1 minus 9x to the negative fifth dx. So then we'll antidifferentiate. The antiderivative of 1 is just x. The antiderivative of 9x to the negative fifth is going to be 9x to the negative fourth divided by negative 4. And I would rewrite this as x minus 9 over 4x to the fourth plus c. Okay, now we want to say so this is what we were saying f of x is equal to. So then we're going to plug into f of 2. If I plug in 2, I should get 2 minus 9 over 4 times 2 to the fourth plus c. And that should equal, well, f of 2 is supposed to equal 4. So now we're going to solve for c. So I'm going to subtract 2 from both sides and add 9 over, let's see, 2 to the fourth is 16. 4 times 16 is 64. So I'm going to say that c is equal to 4 minus 2 plus 9 over 64. So that's equal to 2 plus 9 over 64. 2 is 128 over 64. So this is 128 plus 9 over 64. That's 137 over 64. So c is equal to 137 over 64. Important point. We are not done with the problem, even though we found all the things. The final answer that we need to write is what your actual function is. So our final answer is f of x is equal to, what have we got here? Sorry, I lost my spot. The function x minus 9 over 4x to the fourth plus the value we found for c. So x minus 9 over 4x to the fourth plus 137 over 64. And that would be our actual final answer. Let me see. So someone's asking, can you explain why the sign changed from negative to positive when first integrating? So, oh, you're totally right. I made an error. That's what happened. Right? This was a minus sign and I lost it right there. So let's go back and fix it. So that should have actually been a minus sign. Yeah, no, of course, always, right? If I make a mistake, call me out because I don't want to be telling you guys the wrong things. And I'm a human, I make mistakes. Seems like more lately than in the past. Actually, no, not currently. Like last quarter, the quarter before, I felt like I was making a lot of mistakes. I feel like I'm back to my normal level of occasionally making mistakes. So that's a minus, so it should actually be a plus here. We have a plus here, which means when I bring everything over to solve for c, c should equal 4 minus 2 minus 9 over 64. But yeah, please do always, if you think there's a mistake, let me know. You can let me know in a private message, you can let me know in the regular chat, I don't care. But if you're not sure, you might want to use the private message. Like, oh, you're wrong. I'm like, no, actually, I don't. But yeah, if I made a mistake, please, please, please let me know. So that should be 128 minus 9, and that's going to be 119 over 64. There we go. Much better. So that's how you do a problem like that. So I suppose I should ask you guys then, the midterm you all having on Friday is the material that's on homework 3 going to be on that midterm? Yes. Okay, then we should definitely talk about it. Good to know. That seems interesting though, because the midterm is like in 3 days, right? This Friday. We get you to, okay. But it seems to me that the midterm is on this Friday, but the homework that the midterm is also on is due next Wednesday. Okay. All right, such is life. That's the quarter system for you. So let me see here. Got all that. Yeah. Yeah. So let's look at, so some people ask questions. Someone asked a question kind of like this. What's the integral of x squared times x minus 3? For things like this that don't have too many pieces, we can just multiply it out. This is going to be the integral of x cubed minus 3x squared, which is going to be x to the 4th over 4 minus 3x cubed over 3 plus c. And then we should definitely cancel those 3's. And get x to the 4th over 4 minus x cubed plus c. See what else. I feel like I've hit most of the things people were asking about. Let's look at maybe 1 or 2 more. Let's say we have the integral of, sure, x squared plus x to the 6th minus 1 over x times the square root of x. This is still the same stuff we've been dealing with today. We just have to do a little more. So to simplify the denominator, x times x to the 1/2, right? That's what we have. That's going to be, in fact, let me use a different color here. This here is x to the 3/2. With x to the 1st times x to the 1/2. We add the powers, and 1 plus 1/2 is 3/2. So now we're going to rewrite this integral as the integral of x squared over x to the 3/2 plus x to the 6th over x to the 3/2 minus 1 over x to the 3/2. And then we're going to simplify. We have to simplify something. We're going to use just x to a power before we can antidifferentiate those things. Right? There is no antiderivative quotient rule. We can't, there's nothing to do here except for simplify. So let's see. 2 minus 3/2 is 1/2. 6 minus 3/2, okay, 6 is 12/2. 12/2 minus 3/2, 12 minus 3 is 9. So that's going to be plus x to the 9/2. There is no x here, so we just bring this up to the numerator and change the sign to the opposite. So it's going to be minus x to the minus 3/2. And then we're going to antidifferentiate using the antipower rule. So we're adding 1 divided by the new power. So here we're going to get x to the, let's see, add 1 to 1/2, you get 3/2. Divided by 3/2 is the same as multiplied by 2/3. Plus, here we're going to get x to the, let's see, 9/2 plus 1 is 9/2 plus 2/2, which is 11/2. Divided by 11/2 is the same as multiplying by 2/11. Minus x to the negative 3/2 plus 1, so negative 3/2 plus 2/2 is negative 1/2. So you get x to the negative 1/2 divided by negative 1/2 is the same as multiplying by negative 2. So since I'm multiplying by negative 2, but I have a negative, I'm going to say it's minus a minus 2 or plus 2. Let's see. I think that sure. There's one more. There's one other one that someone asked me that seems different enough. And then I think we should spend the last 10 minutes talking about, and actually, yeah, let's go ahead and talk about u-substitution for a minute. So yeah, we definitely should. Here is where we are going with things, and that's not actually. Actually, let's do that. So I want to find this integral. The integral of 5x to the fourth times x to the fifth plus 1. And we could totally multiply it out first. We say, okay, this is, let's see, 5x to the fourth times x to the fifth is 5x to the ninth plus 5x to the fourth. And we could totally get, let's see, 5x to the 10th over 10 plus 5x to the 5th over 5. Let's see, which ends up being, x to the 10th over 2. I feel like I'm forgetting a piece here, but maybe not. No, I'm not. Plus x to the 5th plus. Perfectly legitimate. However, there's another way you can do it. So this is what's called substitution. So we can write this and say, well, look, the integral of 5x to the fourth, x to the fifth plus 1. This part here, this x to the fifth plus 1, its derivative is 5x to the fourth. So that's what we look for when we start talking about, can we do a u-substitution? Is there something in your integral whose derivative is also present in your integral? So we're going to say, we're going to let u equal that. Okay. So u is equal to to x to the fifth plus 1. And we're going to take the derivative of that. Du dx. And now we chose u because we know the derivative is already there. The derivative of x to the fifth is 5x to the fourth. And typically, what we usually use, we kind of abuse the notation here, and we say, oh, I'm going to say that du equals 5x to the fourth times dx. And look, I exactly have that. This piece here with this piece here, those combine together to exactly give you our du. So look what we're going to do. We're going to rewrite this integral as the integral of u times du. So we're integrating the variable u with respect to the variable u. Something important to remember, when you do a u-substitution all of the variables that were x need to all become u. You can't have anything that's not a u variable here. So now, what's the antiderivative of u to the first power? I'm just going to use the antipower rule and get u squared over 2 plus c. But now, since our integral actually started in terms of x, it also has to end in terms of x. So I need to replace that u with what it's equal to. And u is x to the fifth plus 1. So I'm going to rewrite this as x to the fifth plus 1 quantity squared over 2 plus c. So now here's an important question. Is that the same as that? Let's find out. Let's multiply it out. So if you multiply out x to the fifth plus 1 squared, here's what you get. You're going to get, so when you do like a plus b squared, it's a squared plus 2ab plus b squared. So we're going to get x to the fifth squared, which is x to the 10th, plus 2 times x to the fifth times 1, so 2x to the fifth, plus 1 squared, all divided by 2 plus c. If I write each thing divided by 2, I get x to the 10th over 2 plus 2x to the 5th over 2 is just x to the 5th plus 1 over 2 plus c. So let me ask you guys, are these the same? Yes or no? I would like to see a few more answers. A couple people said something. A couple more people. Guys are like, no, not going to give it to you, James. Not going to answer it. You're very, very, very easy to answer question. And really, it's easy to answer because technically, I would say both answers are right. Right? You could say, James, no, they're not exactly the same. And that would be correct. You could say, yes, James, they are the same enough because this 1/2 plus c is still just a constant. And so what I really want to say here is that sometimes your antiderivatives might look a tiny bit different. How different? A constant's worth of difference. Right? These are different by that constant 1/2. You could say, really, they're not different, James, because this constant here, I'm going to call C1, and this constant here is C2. Those are what are really different. And so this and this are actually the same. But to say this more specifically, occasionally there are some integral problems where you might do one method and someone else might do another method, because there's occasionally problems where two different methods work just fine. And your answers might look just a tiny bit different. You'll be different by a constant. That does happen on occasion. Just be aware of that. So the idea with u-substitutions is that we're trying to look for something to let u equal the something whose derivative is also showing up. So I think I can squeeze one more thing. So sometimes there are problems where you cannot multiply it out. Let me give you two examples and we'll call them a day. So there's this problem, the integral of, say, I don't know, 3x squared times x cubed plus 1 to the 99th power dx. Technically, you could totally multiply that out, but it would take you forever. Yes, to Marshall's question, yeah, if you take the derivative of both of those things, you get the same answer, which means yes, they are both antiderivatives of that function. This one technically could be multiplied out. You should never multiply this out. You should do your substitution. And then something like this. Let's say x cubed times the square root of x to the 4th plus 6. This one you could not multiply out at all. You would have to do the u-sub here. Let's do both of them very, very quickly. So there's two ways to think about choosing your u. Thing one, you want the derivative to also be showing up. So with that in mind, I'm going to choose u equal to x cubed plus 1. The second way we determine how we should choose u is u is often stuck inside some other function, meaning this x cubed plus 1 is stuck inside the function of being raised to the 99th power. Or this thing I'm going to choose for you in this next problem is stuck inside the square root. Or sometimes it's stuck inside an exponent or in the denominator. Basically, if it's somewhere where you can't kind of manipulate it freely, like we just can't multiply that 3x squared through because you've got that raised to the 99th power. That's a good indication that the stuff inside that function is an excellent choice for you. So here u is x cubed plus 1, du dx is 3x squared. So du is equal to 3x squared times dx. So we've exactly got our du right there. And I will say this a lot. It's really, really a good idea to take care of making sure you see where du is coming from first, and then deal with the rest. And then this is our u. So our integral becomes the integral of u to the 99th power times du, right? Because all of that is taken up with the du. And to differentiate u to the 99th, we get u to the 100th power divided by 100 plus c. And then plugging back in the fact that u is equal to x cubed plus 1, our final answer is x cubed plus 1 to the 100th power divided by 100 plus c. And that's how we would leave it. And you can totally check that the derivative works, right? The derivative of some stuff to the 100th power is 100 times our stuff to the 99th power times the derivative of the stuff, which is exactly what we get here. 100 times our stuff to the 99th power times the derivative of our stuff, and then we're dividing by 100 to cancel the hundreds. What u-substitution really is it's how we undo the chain rule. Right? So basically you're saying, oh yeah, this is like my stuff, and this is like the derivative of my stuff. And that's what's happening. Same kind of idea. This one's not quite as perfect. I'm still going to let u equal the stuff inside the function, x to the fourth plus 6. But then my derivative, du dx, is 4x cubed. And I don't have a 4. So what am I going to do? Well, I'm going to say that du equals 4x cubed times dx. And then I'm going to divide both sides by 4. 1/4 du equals x cubed dx. Great, that'll work out perfectly. The kind of rule of thumb here is that if there's a constant multiple that we're off by, we can always adjust for that. So really, when I'm looking for u, if I'm thinking back to my choice of u, I'm really hoping that there's an x to a 1 less power than that for my du, and there is. So this part here, right, all that's going to be my 1/4 du. So I end up with an integral that is, I've got 1/4 du, and then I've got the square root of u, or I'm going to write it as u to the 1/2. And I usually encourage you to put that 1/4 constant multiple out in front. So there's my 1/4 du that's equal to x cubed dx, and there's my square root of u that's equal to the square root of x to the fourth plus 6. Now we antidifferentiate. We get 1/4 times u to the 3/2 divided by 3/2 is the same as multiplying by 2/3. And let's simplify this really quick because we're out of time. 1/4 times 2/3 is 2/12, which is 1/6. U is x to the fourth plus 6 to the 3/2 plus c. That would be our antiderivative.